Hi, this is Mrs. Vrobel. This is part one of the electrons and atoms for chapter 5. This is probably one of the more colorful sections of chemistry where you get to see a lot of light, work with a lot of different compounds and find out what are the electrons doing within the atoms. If you've ever gone to a fireworks display, you've actually witnessed what happens to electrons and atoms. So the colors that you see that are associated with the fireworks are due to those electrons moving in specific ways. Okay, in order to understand what's going on, we first need to discuss light. And please remember that light is pure energy. It will cause certain things to happen, like outside it's a sunny day today, so if I was to wear something black, I would probably notice in a short period of time that I'm getting warm, and that's essentially because that energy is being absorbed by the clothing that I'm wearing. That's why typically in the summertime you want to wear light colors because you don't want to be sweating it out too much. So like I said, it is pure energy. It's important to remember that light contains visible and invisible. So we cannot see all of the energy that is being generated, and we'll talk more about it in a little bit. Please remember, and for those of you that have taken astronomy, that we're talking about 3 times 10 to the 8th meters per second. And that's in a vacuum. So what actually does happen over time, light will slow down when it interacts with gases, maybe a liquid, and obviously with solids. Light can bend. That's what refraction means. So you may notice that when you're looking at the swimming pool, that your feet kind of look funky. If you were to look at an object through a liquid, it's going to bend a certain way. Glass acts as a prism, so it actually bends the light as it enters through the material. Now notice that red light is bent the least. This is the reason why there are red sunsets. This is yeah, I'm going to go back. Yeah, ignore that S, I apologize. What happens with the atmosphere, and I think I've explained this in other classes, all of the other wavelengths that are shorter get bent first, and red is the last visible color that we see, and it gets bent the last. So that's typically why you see the red sunset. So its wavelength is the longest. Violet bends the most. So violet actually is the first color within a prism that gets bent because it's the shortest wavelength of those visible colors. And the light causes this photoelectric effect. You know what, I'll just go on to the next slide here. I want to show you an everyday example of photoelectric effect. So your solar-based calculator is undergoing photoelectric effect. If you open a door with one of those sensors, so if you go to the grocery store or a department store and they have those automatic door openers, that's using the photoelectric effect. So what happens, and this is something that Einstein had figured out. This was one of his great discoveries along with relativity. So what happens is you need to have a minimum energy, and that minimum energy, when it strikes a metal, and it has to be a certain type of metal, you actually get electrons that are leaving the metal atoms. So like I mentioned before, if you have lights that automatically come on, I have one of those night lights that when it sees a person moving or an object moving around, it will actually come on. there's a lot of interesting applications for that. Now, let me just show you how this works. Okay, so here I have a light source, and the intensity, I made it 100%. Now this is violet light, and I'm going to turn it on here. And here you see the violet light is causing the metal to eject electrons, and these electrons are actually completing the circuit, so it's generating a current. If we wanted to power something, we would put it in this circuit, and we would make it do whatever we want it to do. The interesting thing is, too, if you go into the UV section of light, look at all those electrons that are being ejected. So UV is actually a shorter wavelength than violet visible light, and it's causing all these electrons to be generated into a circuit. So this kind of gives you a clue about what's going on with light. Okay, let's go back. So like I said, photoelectric effect, we have a certain type of light. It has to be higher in energy. So you're going to find violet light, which is shorter wavelength. It's higher in energy. It's going to eject an electron, and then that electron is going to complete a circuit for whatever device you're trying to activate. Now, in order to understand this, we need to talk about waves. So we're talking about waves on a seashore or sound waves. Notice that they're a flow of energy. For light, we're looking at wavelength, and it's essentially the distance from crest to crest. So that means the top of the wave to the top of the wave. And wavelength will always be represented by this interesting Greek symbol called lambda. Now, in order to determine wavelength, we also need to look at frequency. Frequency is how many times does that wave occur, and it means from crest to crest. It has a symbol called nu. It's like a fancy looking V. You may see it in 1/seconds or hertz. So lambda, we're looking at wavelength. Frequency, we're looking at how many times does that wave occur. And then lastly, we're looking at amplitude. So amplitude is the height of the wave. So we're looking at where the wave started. So maybe in the middle to the top of the wave, that would be the amplitude. Okay, here is a diagram of the wave. So notice that wavelength, white. Wavelength, we're talking about from the top to the top of the next wave. Amplitude is from the center or where the wave started to the top. I'm sorry, I guess I was trying to do here. When we're looking at velocity or speed of the wave, notice we can take the wavelength times the frequency. How many times does it go through a cycle? Now, you might ask yourself, why do I need this? Well, we're going to do some calculations with it eventually. Now, there was a man by the name of Maxwell. He came up with the wave theory of light. So he determined that light has no mass, and it's electromagnetic. So it actually has two components. So notice that the electric field is perpendicular to the magnetic field. So the electrical and magnetic fields are always going to be perpendicular to each other. Okay, so this is the last slide that I want to show for this section of electrons and atoms. Now, this is essentially the whole electromagnetic spectrum, and I'm sure you've seen this before. This is Roy G. Biv. I would make sure that you know that because you may need to know the order of the colors. Notice that violet has the shortest wavelength. It's only 400 nanometers, and red has the longest wavelength. All of this light travels at 3.0 times 10 to the 8th meters per second. A lot of people think that some light moves faster than others, and that's not the case. The only time it changes is if you're going into different medium, so please remember that. When we're looking at the electromagnetic spectrum, gamma rays are the shortest wavelength, so they're the tiniest wavelength. Whenever you have short wavelength, you're going to have high energy. So lambda, when it goes down, energy goes up. Notice that over here, radio and TV, we're talking miles long. Okay, so the radio waves are extremely long. The astronomy students that I've taught in the past, you know how big those radio dishes can be, and if they're not big enough, they put them in sequence so they can capture the long, long wavelength. So when we're looking at an increase in wavelength, we're looking at a decrease in energy. I know there's been concern about cell phones. Cell phones operate in the microwave region. The jury's still out whether or not it causes brain tumors, but you could err on the side of caution and use your earbud microphone when you're using your cell phone, but we're talking about low energy. We're not talking about X-rays. X-rays obviously are very damaging to us. They penetrate skin because they have beta and gamma emission. Okay, we know that ultraviolet is not good for us. It damages our retina. Obviously, you develop skin cancer because of it. Infrared, we're talking about heat lamps. So if you work in a restaurant, you may see those red lamps that are over the serving area to keep food warm. And then lastly, I talked about microwaves. Okay, be ready for your video assessment.